Ever wonder what makes something like ChatGPT so good? How it can just understand what you're asking, translate languages fluently, and even write poetry? Well, believe it or not, almost all of that power can be traced back to one single brilliant idea.
Right. That's not an exaggeration. This one single idea is the secret ingredient that really unlocked the entire modern AI revolution. And that idea is called attention.
Now that sounds pretty simple, doesn't it? Just let a model pay attention. But to really get why this was such a complete game changer, we first have to understand the massive problem, the huge brick wall that AI researchers were stuck on for years before this came along.
Okay, so let's set the scene. Imagine you're building an AI for machine translation. Its whole job is to read a sentence in English and then spit out the same sentence in French. It's a classic AI task.
So the standard way to build this was with an encoder-decoder model. You can see the basic idea here. The encoder's job is to read the input, and the decoder's job is to write the output. Now, early on, these models used something called recurrent neural networks, or RNNs. And they had a really critical, fundamental flaw in their design.
And here is the problem. The encoder had to read the entire sentence and then somehow squash all of its meaning, all its nuance, down into one single, fixed-size little package, this context vector. Think about how crazy that is. It's like asking a human translator to read a whole complex paragraph, then immediately forget it, and translate the whole thing using only a tiny summary they scribbled on a Post-it note. Yeah, exactly. It can't. There's just no way. This was a massive information bottleneck. The longer or more complicated the sentence you fed it, the more information just got lost in translation. Literally. Performance would just fall off a cliff. This one problem was holding back the entire field.
But then, a breakthrough. Back in 2015, a paper from a few researchers, Bahana, Cho, and Bengio, came out with this brilliant solution. It was a super clever way to completely smash through that bottleneck by just rethinking the whole process.
So here is the big idea. What if the decoder didn't have to rely on that one single static Post-it note? What if, for every single word it was about to write, it could create a brand new, custom-made summary that focused only on the most relevant parts of the original sentence? It's like letting our human translator just glance back at the original text whenever they needed a little more detail.
So how does this actually work? Let's walk through it step by step. For every single word the model wants to output, it first looks back at all of the input words. And for each one, it calculates a score, an alignment score, that basically asks, hey, how relevant is this specific input word to the word I'm about to write right now?
Okay, next up, it takes all those scores and turns them into what we call attention weights. You can think of these weights like a spotlight. The model is shining a spotlight back on the original sentence, and the brightness on each word depends on its relevant score. The most important words get a really bright light, while the others kind of fade into the background.
And finally, it creates a new context vector. But this time, it's a weighted sum using those attention weights. So the words with a brighter spotlight contribute way more to this little summary. And here's the magic part. This whole dance, calculating scores, creating weights, building a new vector, it repeats for every single word the model spits out. It's got a dynamic, shifting focus. And just like that, the bottleneck was gone.
And this is what it actually looks like in practice. It's so cool. This visual shows the attention weights. The English input is along the top, and the French output is down the side. The brighter the square, the more attention the model is paying. See that really strong diagonal line? That's the model learning on its own to connect the words. Look how when it's writing the French word for economic, économique, it's paying heavy attention to the English word economic. It has literally learned where to look.
This was a huge step forward. But at this point, attention was still just a clever add-on to that old clunky RNN architecture. The next leap, the real revolution, came when researchers realized this clever trick wasn't just a trick, it was the whole show.
So in 2017, a few researchers at Google published a paper with, seriously, one of the most legendary titles in AI history, Attention is All You Need. And it asked a question that was so simple but so powerful it changed everything.
They basically asked, what if we just get rid of the RNNs? The slow, sequential part that processes things one word at a time. What if we could build an architecture based entirely on this attention idea? And that question led directly to what we now call the transformer architecture. And the difference was just night and day. The old way, recurrent attention, had to go word by word, which is incredibly slow, and it had a hard time connecting words that were far apart in a long sentence.
But this new approach, which they called self-attention, could process all the words in a sentence at the same time. It was fast, it was massively parallelizable, and it could draw a direct line between any two words, no matter how far apart they were. It was built to scale. So what self-attention really means is that it lets a sentence understand itself. It's how a model can look at a sentence like, "The cat sat on the mat, it was tired," and figure out that "it" refers to the cat and not the mat. It weighs the importance of all the other words when it looks at each individual word. This mechanism, right here, is the core engine inside the transformer, and the transformer is what powers pretty much every single large language model you use today.
Okay, so let's tie this all together. Let's talk about how this one clever idea completely changed the game and what new challenges it's created.
Getting attention away from those old, slow RNNs was the key that unlocked the kingdom. All of a sudden, AI models could be scaled up to sizes nobody thought was possible. They could finally understand those long-distance connections in language, which is crucial for, actual understanding. It suddenly became possible to process the mind-boggling amounts of text needed to train these things. Plain and simple, this is what sparked the generative AI explosion we're all living through right now.
But all of this incredible power brings a new, really deep challenge. These giant models are often called black boxes. We know they work, and they work incredibly well, but we don't always know why they give the answers they do. And so the next big frontier in AI is all about explainability.
One of the weirdest hurdles is this idea called polysemanticity. It's a mouthful, I know, but basically it means that inside these huge AI brains, a single neuron can actually learn to represent a bunch of completely unrelated ideas at the same time. So the same neuron might light up for concepts related to both Italian cooking and the history of spaceflight. Researchers are now working on really complex ways to untangle these mixed signals so we can get a clearer picture of what the AI is actually thinking.
And that leaves us with a final, really fascinating question to think about. The attention mechanism was this incredible breakthrough that taught machines how to focus. It gave them a tool that kind of mirrors our own intuition. But now, as we try to peer inside these incredibly complex minds we've built, we're left to wonder. We've taught them how to pay attention, but can we ever truly understand what they're really paying attention to?